We're now going to study the concept of limits in calculus. Now, limits are very important in calculus because they're used to define and evaluate the derivatives of functions. And the derivative is really the central theme in calculus. So to properly understand what a derivative is, we have to first understand what a limit is. So let's start with this example. So we're going to consider this function, f of x equals x squared, and we're going to ask this question: what happens to the values of the function f of x as the input values x are taken closer and closer to the number 2 without ever actually taking on the value of 2 itself? So one way to answer this question is to create a table, as we have down here. Now notice in this table we have x values like 1.8, 1.9, 1.99, 1.999. Notice that these numbers are getting closer to 2 from the lower side of 2, or from the left, we say. And then we also have values like 2.2, 2.1, 2.01, 2.001. These values are getting closer to 2 from the upper side of 2, or from the right side of 2. Now down here we have our function values for each of the x values in the top part of the table. So notice if we put 1.8 in for x and square it, we'll get back 3.24. For 1.9, the function value is 3.61, and so on. So if we look at these values, 3.24, 3.61, 3.96, 3.996, notice it looks like they are getting closer and closer to the number 4. But we also have to check and see that the same thing is happening as x approaches 2 from the right. Well, if we look at the function values there, notice we have 4.84, 4.41, 4.04, 4.004. Yes, it looks like they are also getting closer to the number 4. So from this table, it appears that as x gets closer and closer to the number 2, written like this, x with that little right arrow, 2, the function values f of x are getting closer to the number 4, and we'll indicate that like this sometimes. Now we can also use the limit notation to indicate what's happening here. So in this notation right here we use, and it's read the limit as x approaches 2 of f of x equals 4. Or sometimes we can write this as well. We'll write the limit as x approaches 2 of x squared, since our function is x squared in this case, equals 4. So this is limit notation here, and we'll use this to indicate what is happening to a function f of x as the x values are getting closer and closer to some number c. Now in this case we can also see this graphically instead of using a table. Now here we have the graph of the function f of x equals x squared. It's this blue curve right here. And we have our x values on the x-axis right here. Currently our x value is 2.8, and the corresponding function value is 7.84. Now notice what happens to the function values here on the y-axis as the x values are taken closer and closer to 2 from either side. You'll see that these values will be approaching the limiting value of 4. So if we do that, so you see the x values are getting closer to 2, and keep an eye on those y values on the y-axis. It does look like they're getting closer to 4. I can step that in a little more slowly. So you see currently x is 2.02, the function value is 4.08, and then we eventually land right on 4. And the same thing if we let x approach 2 from the left-hand side. what we did previously was let x approach 2 from the right-hand side. Now if we let the x values approach 2 from the left-hand side, these function values here on the y-axis will also approach 4 from below. So just keep an eye on those function values on the y-axis. Notice as x gets closer to 2 from the left, they are getting closer to 4. And then we land right on 4. So that illustrates what's going on graphically. So keep in mind graphically here, when you're thinking of limits graphically, you should think of the x values approaching a number along the x-axis, and you're looking at what's happening to the function values along the y-axis. Are they approaching a particular number? Now, in this case, for this function f of x equals x squared, it's a very well-behaved function. So you might have noticed that if we just plug the number 2 in for x into our function right here, if we put 2 in here for x, we just get back 4, which is our limiting value. And that is true for most well-behaved functions. This is a nice polynomial. Polynomials are well-behaved functions, and you could just plug the number 2 into this function and get your limiting value. That's true for well-behaved functions. But as we'll soon see, that's not always going to be the case. Now, here's a little note down here about how you can create a table on the TI-89 graphing calculator and the TI-83. On the TI-83 calculator, we can just store the function x squared into the calculator and then have the calculator evaluate it like this. So if we just press y equals, we'll store x squared into the y1 register of our calculator just by hitting x. That's the x button right there, and we'll square it. Then we can go back to the home screen, second, and we want the quit right there. Now we can press vars, go over to yvars, select number 1 for function, and number 1 again for y1, and then just evaluate that at 1.8, for example. Close off your parenthesis and hit enter. And if you want to redo that, instead of pressing vars again, you can, there's a little entry, a yellow entry right there above the enter button, second entry, and then you can change the 8 to a 9, for example. Hit enter again, do that again, change the 9 to a 99, 1.99, and so on. And so you see these numbers are getting closer to 4. You can also do this on the 89. The TI-89 is a little bit easier. So here's a TI-89. You can do the same thing. Clear that out. Store x squared into the y1 register. X raised to the 2 power. And then just go back to the home screen and evaluate y. Now you have to type y1 of 1.8. Close off the parenthesis, hit enter, and there you go, 3.24. And then you can change the 1.8 to a 9, and then a 99, and so on. And you see these numbers are getting closer to 4, just like on the 83. So that's how you can create these tables quickly using a graphing calculator like a TI-83 or 89. So based on our previous discussion, we have what we call an intuitive definition for a limit, and it goes like this. If there exists a number L such that the function f of x gets closer and closer to this single number L, now that's an important point, it has to be a single number L, as x is taken closer and closer to the number c without ever actually taking on the value of c. So x just gets very close to it, but it never actually reaches c. Then we say the limit of the function f of x is the number L as x approaches the number c, and we write this. So that's intuitively what we mean by as x gets closer to c, f of x gets closer to the number L. Now we'll make this definition more precise in an upcoming lesson. And it's also important to note, as I said, that it has to be a single number L. Now, as we'll discuss later and eventually prove, for well-behaved functions like polynomials, rational functions, trigonometric functions, radical functions, and their combinations, usually to evaluate a limit as x approaches c of f of x, you can just plug c in for x and evaluate f of c. That's for most well-behaved functions when f of c exists, of course. However, when f of c does not exist, then the limit as x approaches c of f of x, it may or may not exist. So more detailed analysis of the problem will be required. And to illustrate this point, let's consider the next example. In this example, we want to evaluate the limit as x approaches 1 of x cubed minus 1 divided by x minus 1. Now you notice in this case, if we put 1 in for the x in the numerator and in the denominator, we get 0 divided by 0. Now this is an undefined quantity, and whenever you see 0 over 0 appearing in a limit, that indicates that the limit may exist. So more detailed analysis is going to be required. So for this particular problem, we're going to create a table, and we'll also look at it graphically to try to evaluate the limit. So here we have a table. So we have our x values. Notice we have values like 0.8, 0.9, 0.99, 0.999. They're getting closer to 1 from the left. And then we have 1.2, 1.1, 1.01, 1.001. They're getting closer to 1 from the right. And let's see what the function values are doing. Now down here you see we have our function values. These numbers, like 2.44, are obtained by putting 0.8 in for x into the function. You can evaluate that, and you'll see that you get 2.44. Well, notice that as x approaches 1 from the left side, it looks like these values are getting closer to 3. But we have to see if the same thing is true from the right in order for the limit to exist. We must be approaching the same number from the right as well for the limit to exist. Well, we see that that is the case. If we put 1.2 in for x, we get 3.64, 3.31, 3.03, and then 3.003 for our function values, for these values of x. And it does look like these are getting closer to 3 as well. So it looks like we would state that our limit is 3. So for our answer up here from this table, it looks like we would write that this is equal to 3 based on this table. Now we can also see that graphically. If we look at this graph down here, the blue curve here is the graph of x cubed minus 1 divided by x minus 1. And keep an eye on what happens to the values on the y-axis, these function values right here, as the numbers here are taken closer to 1 from the left and from the right. So keep an eye on these function values right here on the y-axis. So it does look like, step that in a little more slowly, it does look like as x is approaching 1 from the left, the function values you see are getting closer to 3 on the y-axis. And the same thing if we approach 1 from the right side, it looks like those function values are getting closer to 3 as well. So no matter how we approach the number 1, it looks like our function values are getting closer to 3. And so that's what we would declare this limit to be. Now let's just note one other thing here. When we're evaluating the limit of a rational function like this one, this is a rational function because it's the quotient of two polynomials. When you evaluate the limit as x approaches c, if you put c in for the x's and you get 0 divided by 0, that indicates that the limit may exist, and so further analysis is required. Now we will look at techniques for proving that this limit is 3 later on. If you have a rational function and you plug the c value in for x and you get something like 2 divided by 0, or any non-zero number divided by 0, that indicates that your limit does not exist. So we would just write DNE in that case. And we will look at this in more detail in another video as well. Now let's take a look at another example. Suppose we want to evaluate the limit as x approaches 0 of sine x divided by x. Now notice also in this case, if we try to plug 0 in for the x, we get the sine of 0 divided by 0, and remember the sine of 0 is 0, so we get 0 divided by 0 again. And that indicates that our limit may exist. So we're going to have to look at this in more detail. Once again, remember, if we had gotten something like 2 divided by 0, a non-zero number divided by 0, that would indicate that our limit does not exist. And we'll look at that question in more detail soon. So what we want to do here is we'll create a table again, and we'll also look at it graphically. So here we have a table. Notice we have x values approaching 0 from the left, and we have x values approaching 0 from the right. And we want to see what our function values are approaching. Well, down here are the function values, 0.993, 0.9983, and so on. Notice that it looks like from the left the function values are approaching 1, but we also need to see what's going on from the right. Well, it does look like from the right these function values are also approaching 1. So no matter how x approaches 0, our function values are approaching 1. And so it looks like this limit up here from the table is 1, and that's what we would write. Limit as x approaches 0, sine x over x is 1. Down here we can see that graphically. Notice if we keep an eye on these x values down here as they approach 0 from the right and from the left, let's see what is happening to our function values here on the y-axis. See if they are approaching 1 graphically. So let's let x approach 0 here and keep an eye on the y-axis values. So as x approaches 0, notice those functions on the y-axis. They do look like they are approaching 1. Step that in a little faster. There we go. Okay, so we see the x values are getting close to 0 now, and the function values are getting close to 1. And there we go. X is almost 0, and the function values are very close to 1. And the same thing from the left-hand side. As x approaches 0 from the left side, notice those function values are still getting closer to 1. And so that indicates that our limit should be 1, as we have up here. Now also notice one other thing about this graph, and this was true about our previous graph as well. Notice how we have a little opening right here, a little circle. That indicates, of course, that our function does not exist when we put 0 in for x. So our graph looks fine, except for right there when x is equal to 0, we have to have a little open circle on the graph of our function to indicate that it does not exist when x is equal to 0. However, the limit still does exist because these values here on the y-axis are getting closer and closer to 1 as x gets closer to 0, as we saw. So that concludes this introduction to limits.